Yeah. Okay. Go.
Okay. So, like I was saying, now that it's being recorded in perpetuity or whatever, if you've taken it, yes? That's a 1 factorial, which is 1, and dividing by it is not worth. We'll just do a quick intro to Taylor series, and I'm not going to motivate them at all. I'm just going to tell them to you as the truth. Okay, so it's the case that any this is a lie, but let's say any smooth and differentiable and well-behaved function. It's the case that if I have a function f of x, okay, and I want to evaluate it at in the neighborhood of some point A, then near a point A, and we'll talk about what near means in a second. F of x equals f of A, okay, plus f primed of A over 1 factorial plus f double primed, sorry, this is times x minus A plus f double primed evaluated at A over 2 factorial times x minus A squared plus f triple prime evaluated at A over 3 factorial times x minus A cubed plus dot. And do you see the pattern? Quadruple prime x over 4 factorial. Okay. Yeah. There's if you don't know this, there's like another part of my lecture later on, which is also not going to make sense. But so this is kind of cool. So if I'm actually going to make the claim that you can pick any A, and as long as you take this out to infinity, these functions will be identical. Okay? But if you say you want to know, let's say you want to know, let's put this differently. But in the points that are less than a unit away from A, this series will converge very quickly, meaning you'll get a very good approximate answer just from a few terms. Because, I mean, think about it. Let's say that, let's say you say A is 5, and you look at 5.2, right? And that's the point. Or maybe you're looking at 5.2 to 5.5. Or, you're interested in the function in that domain. Well, what's x minus A going to be? 0.2. And as you start to take powers of it, what is going to happen to 0.2? It gets small really quickly, right? So each one of these terms is going to get really, really small in the neighborhood of A really, really quickly. So near this point that you pick to expand around, and this point could be anything, this function is going to be a great approximation for the finite polynomial that you end at is going to be a great approximation. Obviously, the entire polynomial, taken out to infinity, they're all the same. Can I ask you a question? Yeah.
Can you swipe it to give me the screen back?
Oh, yeah, sure. There we go.
So, like, over here, there's two links that were posted about Taylor series.
Yeah.
And so, like, this is like a picture.
Oh,
in
totally.
this case, is that like the one approximation, the second approximation?
Yeah. So this is okay. So check it out. This is like a sinusoid or something, and it looks like they're expanding it around this point right here. Does everyone see this? And so what they've done is as you add terms, so the first term is obviously just 0, because that's the constant. The next term is this line, this linear term. And around 0, that's actually pretty damn good. Like, just in here, you just have the red line and the black curve are pretty much the same. As you get farther away, though, it's no longer good. So then you add the next term, which is the squared term, which is this. And you can see that this this follows much better. That actually looks like the cubic term. Anyway, as you keep adding terms, yeah, so there's no square term for this. Does that make sense? Can anyone tell me why there's no square term for this?
That was interesting. By looking at it, you could tell, yeah, it wasn't a square term because like odd function versus even function.
There's a symmetry argument.
And you had like y is what?
There's a symmetry argument. This, yeah, that's exactly what you're saying, right? Like under a parity operation, under inversion of the x-axis, this function is its opposite, whereas the squared function is identical to its
But you can see how they
yeah, yes.
What's a parity operation?
It's just an operation where I make x go to negative x for a function around 0. So some functions look the same, like x squared, and some functions look the opposite, like x cubed. Does that make sense?
Yes, that's exactly what I was asking. Parity.
Yeah. This is actually an interesting, yeah, okay, so slight aside. So let's talk about real life for a second. Physics has symmetries, like this function. The laws of physics fundamentally true. Like, an example of a symmetry in physics is, physics right at this point, is it the same as physics like over here? There's nothing like intrinsically special about any point in space. No, physics is the same everywhere. So that's a great example of a symmetry in physics. Okay, so if I took the whole universe and reflected it in the mirror, so if I did parity to the whole universe, would physics still work the same? Does physics care if you're left-handed or right-handed, is what I'm asking. It does. I know, what? It's like, it's not fair, but it does. It's like a trick, and it just hates you. I got nothing. So, you know how there's like regular matter, and you know how there's like antimatter? Which one is there more of? No, antimatter? No. Are we made out of antimatter? Are stars made out of antimatter? Okay, so just so we're not confused, antimatter is not the same as dark matter. Okay. So antimatter is what happens when you have like an electron with a positive charge, or a proton with a negative charge. And this happens with positrons. Okay, so they're these particles. Turns out, randomly, that if you take so every particle has an antiparticle that you get by reflecting its charge and its handedness. So if you do a charge and parity operation in the universe, you get antiparticles. And it turns out this is a fundamental physical symmetry, sort of, because every particle does have an antiparticle. You can make positively charged electrons in a lab. It's pretty easy. I'm not kidding you. You can do this. And so the interesting thing about these, if you have a positive electron and a negative electron and you like squish them together, their charges can cancel and they can annihilate into photons. Okay. But it turns out there's a lot more regular matter. Most electrons are what? They're negatively charged, right? Yeah. And so the universe happens to favor regular matter over antimatter. It's not equal amounts. Why is that? Well, it's because the universe wants you to be like, whatever. Wow, that was relevant. Let's go back to, yeah, no, but it totally, like, when I learned in college that the universe, like, if you reflected, it would be different, that's kind of got burned, you know? It's like, how is that fair? Okay, for a very general class of functions that most of all the functions you've ever dealt with in your life, these functions are called analytic functions. This is true. When you take complex analysis, you'll run into lots of functions which don't. This is not true for, but you really have to struggle to make it. Okay. So now let's, with this in mind, this Taylor series, let's go back to our example here. Let's say this is A. Okay, and I want to look at oscillations around A. Well, so what's U of X? U of X, and we'll say near X equals A. That doesn't even look like near, does it? Yeah, this is near. It doesn't even look like anything close to that though. That sucks. No. The problem is whenever I erase, do you see how big this eraser is? You gotta gentle. Come on. Oh, hell no.
You can make it smaller.
Oh. So it's closer, whatever. Okay, so what is this going to be? Well, it's going to be U of A. Okay, and we can set that to be 0. You know, we could, if we want, right? We could make the 0 energy point be here just for fun. Doesn't really matter. Plus U prime of A. What was it? Over 1 factorial times x minus a. And let's look at really small oscillations, okay? Like really small. So small that I only really want one term. All right, and for really small, for points really near x, like I said, remember for that example where you saw the line, like the line and the black curve are almost the same. Okay, so we said this could be identically 0, so this term doesn't really help us much. But let's look at this term. What's this term? So we said we can make this just be 0, right? Doesn't really matter. So what's the problem with this term? Is this a useful term? Okay, well, we're expanding around a local minimum. What do you know that's true about minimums?
0 to 0.
Yes. This is identically 0. Not helpful. Great. So we have to go to the next term. All right, this term doesn't go away. And so for any really small oscillations for any potential, if you just look at the neighborhood of a local minimum, it always looks like x squared, right? And essentially, all I'm saying here is that for any small oscillation, and this is the case, I don't know if you guys really burnt this in, but for the pendulum problem, it only works for small. What's my
I can go ahead and show a demonstration of the Taylor series.
Oh yeah, go for it.
If I had access to the.
Oh yeah.
Oh, there we go.
Okay, so so the pendulum that you guys solved that obeys the harmonic motion is only true when small angles. And in the derivation, you probably went over how small the angle needs to be. Yeah. And it really just comes down to the squared term, the potential energy, has to be like orders of magnitude bigger than the next term. So the next term doesn't really matter. So every kind of oscillation you see, if it's a small oscillation, is simple harmonic. So that's why it's important. How long is this
So
process?
this is kind of a cool. You can drag it around.
So that was the first half of my lecture. There's another part, but we don't have to do it. So we'll just look at this.
You can see how the Taylor series approximates this cosine curve as you drag it around.
How many terms are you doing?
This is just a parabola.
So this is 2 terms.
So this is just 2 terms. So you see right here, it's a pretty good approximation of the well. Here, it's a pretty good approximation of where it crosses the axis. Here, it's a pretty good approximation of the maximum.
So you can see within about a unit, within about a unit of the point, it converges really quickly. And that's just to do with when you take powers, successive powers, and something less than 1, you get really small.
But you notice it's only accurate in the local region around where you expand it. Anywhere further out, not very accurate.
But if you want to make it more accurate farther out, what do?
And then you can
Add more terms.
order.
Simple
Instead
as
of
that.
1 to the
Or did you start at 0 when you're doing 2 series?
You can start anywhere.
Here's
So
I know, right? That kind of blew my mind too.
In terms of this being 2 terms, that would be over 1 factorial and then over
Over 2. But the A?
You notice how it's
A
7 and it's always, up and down, right? Because the
on working
everything's
straight.
gonna happen.
Yeah, this is A. This point here, he's picking A. And so the Taylor series, right, if you take infinite number of terms,
it's pretty
the
good.
functions are the same everywhere. But if you take the less, the functions are only the same near A. And you can let A be anything, but they're only the same near A.
Okay.
This is like, you'll derive this, and this is like, there's like a lot of really important stuff. Like Euler's, you guys know like, what's e to the I pi equal? If you take e and you raise it to the power of I times pi. Okay, so yeah, this is you'll learn all kind of fun stuff about Taylor series. Okay, yeah.
Thank you very much. iPads in, please. iPads in. So I'm hoping that one day you're sitting there in calculus or engineering class and you remember to. You'll be like, crap, I remember. Okay, let's go. iPads
It's
in.
important. You should remember it.
Yeah, you should probably log out.
The first time when you're writing that, you write. People are like, but that's good. No.
Yes.